like exactly that. Like I hit so flat randomly, and it's like because like all they're doing is text. Probably. Like what was if I chose like the same thing as certain things? Just like on the last one. I haven't done the last one, so you can compile it. Yeah. It's interesting. Yeah, see, I didn't, I haven't done project 3 yet. And that was just
I'm going to get right to the point. It's come to my attention that you and the cleaning woman have engaged in sexual intercourse on the desk in your office. Is that correct? Who said that? She did. Was that wrong? Should I not have done that? I tell you, I gotta plead ignorance on this thing, because if anyone had said anything to me at all when I first started here, that sort of thing was frowned upon. Because I worked in a lot of offices, and I tell you, people do that all the time. You're fired. Well, you didn't have to say it like that. I want you out of here by the end of the day.
He's saying for project 2 you have to submit a token.
I thought it was project 3.
That's a 2.
Yeah,
I was
project
saying
3.
project 2 you have to use just the Pi file.
Yeah,
Right?
that's true.
Okay.
Okay, let's get started. So the midterm is over. You got to do it at the second time. I think the midterm corrections also you got a chance for that. Project 3 is due this weekend. And then today's agenda is to get you back into the flow of things that we left off, which is basically machine learning. We got into machine learning through reinforcement learning, and after doing online reinforcement learning, we then shifted to classification learning, and we shifted to perceptrons. I want to quickly review those things, and hopefully you also had looked at the videos that I have asked you to look at, so we'll mention those in passing, and then we'll transition to multi-layer neural networks and backpropagation. Okay. So, how many of you know Siraj Raval? A better, well-known, a more known, better known name starts with Rao, but then it's better known as Rao. So, very apparently, he has 69.9 thousand followers, and then presumably he also has started all by himself, having dropped out of undergraduate study because AI is so damn easy. He also started an AI university for the masses. An AI university for the masses, and so he makes new videos every week. I do too, but nobody watches mine. Right? So he makes new videos every week and he has a huge following. He recently also, of course, he monetizes what he gets. He started teaching machine learning in 2 days. Instead of, my God, I mean, machine learning going on and for the whole entire semester, killing you, giving hard projects. It's so much simpler to learn machine learning in 2 days, right? In fact, he even realized that the 2 days machine learning is too much for machine learning. So in fact, in his most recent thing, he also said, he will teach you how to write a paper in a week. A research paper in 1 week. And he basically made 1 week, he wrote his own paper in 1 week called Neural Qubits. And he basically said, this is how you do it. Essentially, you start the word processor and write and it'll be there, right? And obviously, large number of people are thinking, man, this is good stuff. You know, I'm happy that I paid. So it turned out that unfortunately, when you have 64,000 followers, you know, what you can do basically can be looked at by other people, right? And so this guy Andrew M. Webb, who is such a spoil sport, is such a party pooper, that he actually compared this paper that Siraj Raval wrote in 1 week to archive. In case you don't know what archive is for copying papers, what GitHub is for copying projects. And you exactly know what I'm talking about. Those of you who have done this, okay? So he went to archive, took 2 papers, you know, basically, and modified some words, cut some pieces, generated this paper, and presented it. And the bozos who pay him $200, nobody pays me $200 to listen to me. The bozos said, wow, this is good looking stuff. It looks in LaTeX, it looks like a paper. And it seems kind of nice. Okay, because after all, everybody should be able to do AI, and Siraj can do it, and Siraj can tell us how to do AI, right? And so, Andrew Webb, and then basically people started realizing that there were connections to these papers to what he has written, and Andrew, this just happened like less than a week and a half back, in October 30th timeframe. So Andrew Webb basically pointed out that it's not partly plagiarized, it's really 90% plagiarized from these 2 papers. But the format is different. That's important. Plus also the name is different. He wrote Siraj Raval. That makes it his paper now, right? I'm sure you guys know what I'm talking about. If you take a GitHub code, put your name, give it a great score, it's yours, right? Very nice. And then also, of course, you have to change some variable names. Otherwise, it looks as if you haven't spent any time at all. So in his case, he changed some phrases. For example, he took this word quantum gate and he said, let's call it quantum door. Because after all, if you look in synonyms, door, gate, all the same, right? And then he also said, saw complex Hilbert space. After all, he's made his life making complex things simplistic. Okay, so he said complex Hilbert space looks too much. Let's call it complicated Hilbert space. So these are some of the main things that he has done in copying his paper. Okay. Unfortunately, people got mad at him. I don't know why. So then he had to apologize. And so he obviously has seen George Costanza saying, is that wrong? Should I not have done that? If only people told me, I would have done this kind of nonsense. So he put this up on October 13th. I've seen claims that my neural qubit paper was partly plagiarized. It's as if I don't know anything. It's my paper, but things just get written in it. Same way, it's my project, but somehow other people's code just gets into it. What am I supposed to, right? So this is true, it turns out. And I apologize. I made the video on paper in 1 week to align with my 2 videos per week schedule. So really, he should have set himself, make a universe in 1 week, and he would have gotten a universe in 1 week, because everything is done in deadlines. Okay? And he also said, I hope to inspire others. I don't know about what, but I hope to inspire others to do research. This is the kind of research. Moving forward, I slow down and being more thoughtful about my output. Maybe he will change more phrases into, better sounding, nonsensical phrases. Anyway, and Webb says, I made a video on a paper in 1 week is such a nonsensical thing because people spend years writing one paper. People people spend 2 weeks plus more completing the damn project that we give you. Okay? If you are somehow able to complete it, just on the deadline, you are Siraj Rawa without the followers. Unfortunately, stuck in my class, which is not good. Okay? So I made a paper, and any Siraj fans who are reading this, please realize a paper like the one he plagiarized is sometimes the result of a year or more of work on the part of the whole group of people, not the work of one man in a week. Okay? There is no easy way to learn things. There is no easy way to learn things. If you think there is, essentially you got brainwashed by probably watching Siraj Rao's videos. Now, this is what bothers the heck out of me. He's one of the guys who's his fanboys who basically says, he's saying, Andrew, stop ragging on poor Siraj. He apologized. Once you say, I'm sorry, you are supposed to be nice. This is the world we live in. You know, you can screw around and say sorry, go to the next class, do the same thing, and sorry, and go to the next class, do the same thing, and say sorry. Unfortunately, most people have other lives. As I told you, when I teach this course, I have none. I just have this. I tell this in the beginning of the class. Don't test this. And some of you have tested it. Anyway, so here is a way to write a paper. Essentially, it's a code. In fact, some of you who might want to find this and good help so that you can write your own paper, you know, do this. Okay? And so you basically have to take a paper from archive and change a few things. As I said, archive is to paper plagiarism what GitHub is to project plagiarism. Okay? So you start small copying projects, you can have spectacular fall, and people will be talking about you in their classes like this. And if that's what you're working for, you know, continue copying stuff, and you know, what you will pay in this class. As I said, it's possible that I'm just too bitter that, you know, he looks much better than me, he has that nice gray hair. I only have fully gray hair, not on the gray. And even though his name sounds like mine, nobody watches my videos. These are apparently a lot more dancing involved, and they're only 2 minutes long and made of junk, and so people are getting too much. Okay, that's fine. Probably I'm bitter. But so I was, well, Alberto, can you take me some water, please? Okay. So I was quite impressed yesterday, as were every TA of this class. You know, Alberto, Niharika, lots of all of us, after we found several people have essentially assumed that we are paper tigers. So remember I told you that I like to know people's faces to names? I now have an entire last page, which I'm not showing you, that I do have faces to names. These are the cheaters. Okay? So obviously, it's not a good feeling after spending my time trying to teach you, after spending our time trying to set up the exam in a way that makes easier for you to actually do the second time the exam, etc. Finding out that so many people are essentially misusing the system. And they're not only disrespecting the work that the TAs are doing, they're disrespecting all the other people in this class who are actually playing by the rules. You understand what I'm saying? It's not coming easy for them. And so they do have families, they do have lots of credits of coursework, they do have every damn thing that all of you who have cheated would come up with as examples. Okay? But they chose not to do it. And you are not in the grade school. You are, most of you are juniors, seniors, and graduate students. So I was actually very impressed because I spent like the day before, I was like, yesterday morning, before this happened, I was talking about how I'll get more time from you guys so that I can teach you more stuff. And then by evening yesterday, I didn't want to come to the class. Okay, because there's no point, essentially, if all I'm doing ultimately is worse than what Siraj Rao is teaching you. There's no point. Okay. Thankfully, I do know that while there is a whole bunch of people who cheated, there are also a whole bunch of people who are playing by the rules. For example, there's a character who spent the 1.5 days before the exam going through every YouTube video that I recorded. Netflix binge watching replaced by raw binge watching. Okay, and put annotations on where each of the concepts are in this. You didn't have to do this, you just do okay in the exam. Somebody did this. And this morning when I woke up, I got a comment on the SurveyMonkey, and I thought, oh my God, one more some whiner going to say, if only I was told I'm not supposed to copy kind of a thing, and I don't want to see this, deal with this, and turns out this is the comment. Clearly, so this basically says, would you please tell us how what you are teaching relates to your research and other people's research in the university? Okay, now clearly this person didn't want to give their name because they're afraid of being tarred and feathered by the rest of you guys, right? Because, right? But so I teach ultimately because there are people who actually pay attention. And as I told you, I don't have to teach this class, and I'm sure you don't have to take my class either. There are many, many other ways. Okay, I can't stop you from cheating in your life, but for you to think that you can cheat in my class, I don't know how nice I must have looked to you guys. You know, one of my students says that I say so many jokes that people think I'm an easy guy. I can't believe that. Okay, so the people who did, and this is only for those people, I'm very sorry for the other people who had to go through this, but I want to do this as the non-cheaters. This is a sign of respect to you. I actually prepared for this class, and I'm going to teach a class because of you, because of the people who actually pay attention, because of the people who take it seriously, irrespective of whether or not people are looking over their shoulder. Okay, that's that. Okay, so so I'm going to quickly review what we were doing last class about machine learning, and I'm going to go through this quickly because by the end I want to get to multi-layer neural networks. Okay, and I just hope that people will come back to this frame of mind by the end of this. Okay, so anyway, we used to do reinforcement learning, which reminds me there's a great talk on reinforcement learning that is actually at the edge of the state of the art. This is a guy from Didi, which is Uber killer of China. It's like the biggest rideshare organization. The Didi AI group head is Jiping Ye, who used to be my colleague here. He was actually a professor in machine learning here, and he then left after a while, and then he joined Didi and became the head of the AI group. And there is a group, there's a lab for Didi in Silicon Valley, and this guy Tony Chin is working there, and he will talk about how they use reinforcement learning in ride-sharing applications, figuring out how to dispatch what rides to who, okay, which is the thing that they'll wind up doing. So if you're interested in some application, direct application of reinforcement learning, which you would have a reasonable chance of understanding, given the discussion we have made here, you might show up tomorrow to that room I sent. Okay, so we did reinforcement learning. We then started talking about reinforcement learning in the lifted space, that means feature-based representations. And when you have feature-based representations, instead of updating the values when you do either your temporal learning, temporal difference learning, or the Q learning, you'll wind up updating the weights given to the features, where you assumed you were considering the value to be a linear weighted sum of the feature values. Right, that's what we did. Okay, and then we talked about, the question of course is how to change the weights, and the way to change the weights, it turns out, I'm sorry, these are actually the wrong slides. The slides that I should have copied over are the ones that change the weights using the gradient update rule, right? Because these were the ones for the atomic version, okay? So the way to change the thing, the weights would be in terms of the weight update rules, and we talked about how the weights can be minimized by looking at the fact that the weights are a real vector, real valued vector, and you need to minimize the error such that you want to set the weights such that the error between what you predict is the value and what is the actual value of the cell winds up being minimized. So it's a function whose minima you're trying to find. And to find the minimum of a function, you get into calculus, you start doing derivatives, you basically take the differential, and in general, if you want to just directly get the minimum, you take a differential equated to 0 and solve for it, but in most cases, you can't solve these equations where the derivatives can actually be non-closed form and can be actually quite complex, even if they're in closed form. And so you can't directly solve them. So instead you do small steps in the direction away from the gradient. If in fact you are doing gradient descent, which is you're trying to minimize, or you go in the opposite direction if you're trying to do maximization. Okay. In the error minimization, you go gradient descent. In the maximum likelihood maximization, which we'll talk about when we get to probabilistic interpretation of machine learning, you would wind up doing gradient ascent. Okay, fine. So we talked about that, and one other thing that we noticed is that in fact, what was being done there when you are computing the weights, basically setting the weights such that this linear weighted sum minus the actual value squared is minimized. That is basically called linear regression. And you could have viewed linear regression in terms of like a perceptron unit, where these are the features and these are the weights on the features. These weights are being, the features are being multiplied by the weights, and they're being summed, and then they're being passed through. The sum and the summed portion is coming out. And that's how the perceptron is estimating what the value should be. Okay? And what you wind up doing is you set these weights using our approach, the gradient descent, such that what it is estimating for any feature combination is close to what its real value is. That's basically the regression. And I also mentioned that you could also make this nonlinear here. In particular, you could use this same idea to do classification, where the classification would be you threshold the linear weighted sum with a nonlinear function. And we talked about various kinds of thresholds. We talked about step functions, we talked about sigmoids, we talked about, I don't know whether I mentioned, but tan H is another function. And then there is also ReLU, which is rectified linear unit. These are all different ways in which you're making like up until this point, I would send out 0. After this, I will send out the actual value, for example. So it's a nonlinear threshold. Okay. In fact, any nonlinear function can be there. And so if you do use this kind of a thresholding function in the last step, then it actually becomes perceptron. Because originally, a guy called Frank Rosenblatt, when I was born around that time, he basically realized that these kinds of structures, with this kind of a nonlinear thresholding at the end, can be used to classify things. And if you give, for example, here are all the positive examples of, here are all the good students, here are the bad students, can you put a, can you differentiate so that if I describe a student, you can tell whether or not it's a good student. Okay. The question then would be that basically the features of the students are being input and the weights are being automatically computed by the perceptron learning algorithm, such that outcome will always be typically a 1 or a 0 if it's a step function. Right, so the difference between classification and regression is the regression, the outcome is a real number. In classification, the outcome is a categorical number. It's basically integers is the best way to think about it. Right? And you people realize that the space of integers is not continuous. The space of real numbers is. So calculus doesn't work for just integers. Let's keep that in the back of our mind. But anyway, so the integers are what you're using here, and you're getting approximate to integers by using these nonlinear thresholding functions. And in particular, if you were to use a nonlinear threshold function called sigmoid function, then this idea will come very close to a pretty well-known idea for classification called logistic regression. The only difference would be not only would you use sigmoid function as a threshold, but you also change the loss function. Loss function is what you are minimizing. Previously we decided the loss is the error, and we took the squared error, half of the squared error, and we minimized it. Remember the half of the squared error and we minimized it. If on the other hand, you take what's called a cross entropy loss, which we'll talk in a minute again, but in essence it basically assumes that what is supposed to come out is a probability distribution, and you're comparing it to another probability distribution, the true probability distribution. Okay? And then trying to minimize the distance between these two probability distributions. Notice that the probability distributions are also numbers, except they have special properties. They actually fall in what's called a simplex, which is a simplex is part of any space where the coordinates of all the points sum to exactly 1. Okay? Anyway, so in this particular case, you could actually use cross entropy loss, and you could use sigmoid function, and then you would have perceptron doing logistic regression. It's a different approach that came from a different place, but really you can think of it as connected to just, you plug and play. You plug a different, loss function, plug a different threshold function, you get a different learning of that. Okay? So anyway, so we talked about the connections between perceptrons and neurons. Very, sort of, there are some kind of connections because neurons do seem to have, the neurons in the brain seem to take activations from other neurons, and they seem to gate them. That's where the word gate in the previous thing comes. Gating essentially is a thresholding behavior. Okay, so originally when this guy looked at these kinds of units, he said, hey, this looks like neurons, individual neurons doing great stuff. Now I should be able to do everything that humans can do. This is what, Rosenblatt was very happy about. There are also some interesting, first of all, one piece you want to remember is that, so basically, current day neural networks have extremely little to do with the brain, except the word neural. Okay? It's like the other thing, the genetic algorithms as basically the word genetic, and some people will fall for it, essentially. And so it's like a sort of an analogy, but really the real neurons don't do most of the things neural networks do. We will keep talking about this multiple times, okay? But the analogy has helped people in coming up with some things. Okay, so anyways, as I said, da is sort of like a neuron. It actually isn't, okay? And most neurologists basically still do not agree that the brain works anywhere like this. But on the other hand, neurologists don't know, neuroscientists don't know how the brain works anyway. Right? So it helps because you tell them, hey, you have no idea, at least we have something that's working, so what can I take this? Okay, anyway, so you remember this distinction between regression and classification I mentioned, that's also part of the review. One other last piece that's part of the review that I want to mention is, in addition to having computed the update rule, weight update rule for the linear regression, I also showed you how we could have computed the weight update rule for a perceptron which is using basically any thresholding function, let's say sigmoid function, g of x, and is using RMS error, the mean squared error. RMS actually is the wrong thing, root mean squared, but I mean, we're looking at the mean squared error. Okay, if you minimize mean squared error, you also minimize root mean squared error. That's not a big issue. But we went through this, and that's one of the last things I did when we went off for fall break. And the thing you want to remember about these kinds of derivations, they're all the same. They are all essentially wind up using chain rule of differentiation. They just use chain rule of differentiation. You're trying to compute the differential of the error with respect to some quantity, in this case a weight. Right? And what you wind up doing, so in this particular case, this is the error and I want to compute the partial derivative of this error with respect to the jth weight. And that tells you how much the jth weight should be changed. The negative of that tells you how much the jth weight should be changed. Do you see what I'm saying? And so one of the interesting things is, when you got this, you realize that it is connected to t minus o, which is the error term itself, g dash, which is the differential of the thresholding function, right? And ij, which is the input corresponding to the weight. Interestingly, if you remember this, they will always be sort of true. Even when you go to multi-layer networks, you will wind up seeing there will be an error part, there will be the g dash corresponding to the thresholds differential, and there would be something corresponding to the input. The only thing, sort of giving away a little bit, is when you have multiple layers. I know that we haven't specifically formally introduced multiple layers, but you are all thinking about it all the time. If you have multiple layers, what happens is that there is another layer before here. That's where the real inputs are coming, which then become intermediate layer activations, which then are affecting the final layer. So as far as this guy is concerned, its inputs are actually the activations of the previous layer. So in fact, instead of the I term, you will wind up having the A term, the activations from the previous layer. This is how they all look. So as far as you are concerned, you can be sure that that's how the gradients will look, but somebody has to have proved it once. So we will prove it today for a two-layer network. But then having proved it, we will point out that since everybody has become impatient and nobody wants to learn anything from first principles, and after all, everybody expects, I mean, the number of emails I get from high school students saying they want to do state-of-the-art AI research, because anybody can do it. Siraj Rawal told them that, right? It's just amazing. I don't know what's wrong with you guys. You never send me any emails saying you want to do research. Maybe you got beaten down or something, but apparently high school students are thinking this is where anybody can do. And when they say anybody can do, they don't know what the heck is a gradient necessarily. Maybe in some better schools they do, but mostly they don't. But they know how to start TensorFlow, put in some numbers and look for some numbers and plot. And especially if there are science phase, this is my unfortunate, I know I'm like a cynic, especially cynical today, but if you go by the science phase, cancer has been basically cured about every year about 10,000 times. If you look at the science fair things, this little girl and this little boy cured cancer. Next year again they get to cure it.